When people first decide they want to transition into machine learning, uh, they almost always picture this highly glamorous side of the field.
Oh, absolutely. They
Yeah.
see themselves architecting massive neural networks or, you know, deploying AI to predict the stock market.
Right, exactly. Or building these crazy generative models. But if we just strip all of that away for a second and look at the actual day-to-day reality of a working ML engineer, the picture is, well, it's pretty different.
Yeah, it really is. It's much more grounded.
So let's talk about the absolute core reality of real-world machine learning workflows. Like, what is the very first technical action an engineer takes after they, get their credentials and connect to a brand new, completely undocumented enterprise database?
I mean, I'll tell you what they don't do. They don't immediately start importing TensorFlow.
No, definitely not.
They don't begin engineering complex features, and they certainly don't start training models. If they tried any of that right out of the gate, they'd be flying completely blind.
Yeah, it'd be like trying to build a house without ever actually looking at the dirt you're pouring the foundation on.
That is actually the perfect way to frame it. The very first thing they do is simply look at the data.
Right.
They ask the most fundamental, just structural questions imaginable, like what columns actually exist in this environment? What does a typical single row look like?
What type of information is actually being stored here? Right.
Exactly. And honestly, what is missing? This crucial first stage happens long before any fancy AI math gets applied.
And this is known as data exploration. Mastering these tools is, well, it's completely non-negotiable if you actually want to survive in a production environment.
100%.
So, with that being said, welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry ready and apply your knowledge to real industry projects.
It's fantastic to be joining you for this deep dive. That
Yeah.
opening premise perfectly captures the stark reality of the profession,
Mm.
you know,
Yeah, it really sets the stage.
because you could be the most gifted Python developer on your team, right? You could understand the calculus behind backpropagation flawlessly.
But if you don't actually know what your data looks like,
Exactly. If you don't possess a systematic method for understanding those raw underlying data structures, your predictive models are doomed before they even compile.
and addressing that exact vulnerability is the core mission of today's deep dive. We are putting a huge magnifying glass on the fundamental SQL operation that serves as the engine for all data exploration.
And that operation is the select command.
Right. Our objective today is to help you build a rigorous, rock-solid mental model for how professional ML engineers extract raw information from massive tables. We're going to explore how they systematically understand the environment they've been dropped into well before they ever write a single line of their machine learning pipelines.
To properly contextualize why we are spending an entire deep dive on literally one command, we really need to talk about the sheer scale of modern industry datasets.
The scale is just mind-blowing.
It is, because when you are first learning basic Python or following introductory data science tutorials online, you are almost exclusively working with tiny, highly sanitized CSV files.
Right, like the classic Titanic data set or something.
Yeah, exactly. You might have a file with, 500 rows and 10 columns. When you have data that small, you can literally just open it up in Excel or whatever basic spreadsheet app you use.
You just scroll through it.
Right, you visually scan the columns and use your own human intuition to understand the patterns. But that approach completely shatters the moment you step into a real enterprise environment.
Because an enterprise database table doesn't have 500 rows.
Not even close.
Yeah.
It routinely contains hundreds of millions or even tens of billions of rows distributed across complex cloud architectures.
Billions. You physically cannot just open that up on your laptop.
No.
Even attempting to load a billion rows into your local machine's memory would instantly crash your entire system.
Without a doubt. So to make sense of a data set of that unimaginable magnitude, you need a different paradigm entirely.
Okay, so what does that paradigm look like?
You need a way to systematically inspect specific columns, pull down small, highly manageable samples, and probe the underlying architecture without moving the entire mountain of data.
And the SQL select command is the foundational tool for that.
Precisely. It allows you to instruct the database engine to isolate and return only the highly specific microscopic slice of information you require.
Let's get right into the mechanics of how that actually works. The first major conceptual hurdle we need to cross is a process called projection.
Yes, projection.
In the architecture of relational databases, the act of selecting specific, targeted columns from a much wider, denser table is formally referred to as projection. And practically speaking, this is like step zero in dataset construction for any ML project.
The terminology there is actually quite elegant if you think about
How
it.
so?
Well, when you think of a literal projector in a movie theater, it takes a highly specific image and casts it forward onto a blank screen, right? It just ignores everything else around the film strip.
Oh, I see where you're going with this.
In SQL, you are shining a light on a specific vertical slice of the data, say, just 3 columns out of a possible 300, and projecting only those 3 columns onto your screen, leaving the other 297 columns behind in the database.
I really like that visual, but let's ground it in a mechanical analogy so we can really see why it's so critical for machine learning specifically.
Sure, let's do it.
Think of a massive mixing board at a live concert. You've got 100 different audio channels coming into that board simultaneously. You have 5 different microphones on the drum kit alone.
Right, plus guitars, vocals, everything.
Exactly. 3 separate guitars, the bass line, the lead vocal, the backup singers, the synthesizers, and even microphones capturing the ambient noise of the crowd. Now, if the sound engineer just pushes all 100 faders up to the maximum volume all at once, you don't get music.
You just get this deafening wall of noise.
A total wall of chaotic, incomprehensible noise. So projection is the act of that sound engineer isolating specific channels. They pull down the faders on the crowd noise and the rhythm guitar because those just aren't needed right now, and they solo the lead vocal and the piano.
You are selecting only the specific signal channels you need to create the final mix.
Exactly. And that is a highly accurate parallel to feature selection in ML.
It really is. And the way we operate those faders in our database environment is through a highly readable SQL syntax. The fundamental structure requires you to declare the action, declare the targets, and declare the source.
Okay, break that down for me.
You write the keyword select, followed immediately by a comma-separated list of the specific column names you want to isolate.
And then?
Then you follow that with the keyword from, and finally the table name where the data actually lives.
So applying that syntax to a real-world scenario. Let's say we have an incredibly dense enterprise table called users. It tracks everything from their unique ID, age, and geographical country to, their exact browser version, the microsecond of their last login, their referral code, and 50 other highly specific tracking metrics.
Which is very standard for a production table, yeah.
Right. But if we only care about their core demographics for, say, a basic clustering model, we'd only want a few of those.
Exactly. You would literally just write, select user ID, age, country from users. It is entirely declarative. You are not telling the database how to find the data. You are simply declaring the exact vertical slices you require.
And the mechanical impact of that query is instantaneous. You start with this incredibly wide, chaotic table containing 60 different columns of varying relevance.
You just cut through all of it.
Yeah, you execute that projection, and the database engine processes the request and returns a pristine, narrow data set containing only user ID, age, and country.
Now, connecting this directly to the architecture of machine learning models, why is this isolation so critical? Because it goes far beyond simply making the data look cleaner on your monitor.
It's about the math, right?
Yes. It ties into a foundational law of data science, the curse of dimensionality, and the principle of garbage in, garbage out.
Right. Because a machine learning algorithm at its core is just a mathematical optimization engine. It does not possess human common sense.
None whatsoever.
It can't look at a column called random session hash and intuitively know, oh, that's irrelevant to predicting user behavior.
The model just sees a matrix of numbers and text, and aggressively attempts to find statistical correlations between them, completely regardless of what they actually represent in the real world.
Precisely. If you are training a neural network to predict whether a user will upgrade to a premium software subscription, their age and their country might carry incredibly strong predictive signals. But the exact microsecond they first loaded the homepage, or the randomized string of characters in their temporary session cookie, that is pure, unadulterated noise.
And if you allow that noise to flow into the algorithm's input layer, the model will waste vital compute cycles trying to learn it.
Which is bad enough on its own.
But worse, it might accidentally find false, spurious correlations in that noise, leading to massive overfitting.
Meaning the model will just perform terribly on any new real-world data.
Exactly. So projection is your primary defensive shield against this. It mathematically reduces the dimensionality of your input space, eliminating the noise and preserving only the high-value signals.
That makes total sense. We use projection to strictly curate the signal,
Yeah.
but that brings up an immediate practical problem for me.
Okay, what's that?
When I first connect to a totally alien enterprise database, I don't inherently know which columns contain the signal and which contain the noise.
That's a very fair point.
I might not even know what the columns are named. I don't know if the table uses userage or just age or, I don't know, customer demographic age.
You're completely guessing at that point.
Right. So before I can cleanly project 3 specific columns, I kind of need to see the whole board. And I know there's a widely used shortcut for this, the asterisk operator.
Ah, yes, the select command. It is simultaneously the most useful and the absolute most dangerous tool in the SQL ecosystem.
Okay, let's talk about the useful part first. If you write select from users, that asterisk acts as a universal wildcard, right?
Yes. It essentially commands the database to select every single column that currently exists in this table.
And for a human being who is just, poking around a new database, it's an incredible time saver. You fire off that one simple query and you get a sweeping panoramic view of the entire schema,
You can see all 60 columns lined up side by side.
which allows you to figure out what data is even available to you in the first place.
For initial manual reconnaissance, it is indispensable. Every single data professional uses it when they are visually orienting themselves in a new environment.
Okay, but this leads me to a devil's advocate scenario. If select is so powerful and it guarantees that absolutely no data is left behind, why don't ML engineers just use it in their actual production code?
Oh boy.
I mean, why go through the tedious process of manually typing out a list of 40 specific column names for a feature pipeline when a single asterisk does the exact same thing dynamically? If deep learning models are so advanced, why not just dump the entire asterisk output into the pipeline and let the neural network's hidden layers figure out what to ignore?
That line of thinking is incredibly common among junior developers who are transitioning into data science.
I mean, it sounds logical at first.
It does, but correcting that assumption is exactly what separates a hobbyist from a professional ML architect.
Okay, hit me. Why is it so bad?
Using select inside an automated production machine learning pipeline is not just bad practice. It is a literal ticking time bomb that will eventually destroy your production system.
A ticking time bomb. That seems like really strong phrasing for a wildcard operator.
Yeah.
What is the actual mechanism of failure here?
To understand the failure, we really have to look at the intersection of database architecture and machine learning engineering. We have to discuss the concept of the database schema.
Okay, the schema.
The schema is the strict structural blueprint of a table. It dictates exactly how many columns exist, what their names are, and the exact order they appear in.
Right.
Now, in a dynamic, growing tech company, that database schema is not a static artifact. It is constantly evolving. Upstream software engineers and data engineers are continually modifying it to support new application features.
Because the business requirements change. Like marketing wants to track a new metric, so engineering just adds a new column to the main table to store it.
Exactly. So let's trace the exact anatomy of this disaster scenario. Imagine you are tasked with building a fraud detection model. You build your training pipeline, and to save yourself some typing, you use select from transactions to pull your data.
Makes sense so far.
At the time you write this, the table has exactly 20 columns. You train your algorithm on those 20 columns. It achieves excellent accuracy.
You're feeling pretty good about yourself.
Very good. You deploy it to the live production server. Now, every single minute, your automated inference pipeline executes that select query, pulls the latest transactions, feeds the 20 columns into the model, and predicts fraud. Everything is running flawlessly.
Until the schema changes.
Exactly. Fast forward 3 months. A back-end data engineer, working on a completely different team, receives a ticket to track which mobile operating system a transaction originated from.
Oh, no.
They run an alter table command and insert a brand new column called device size right into the middle of the transactions table. And they don't tell you because they have no idea your ML pipeline relies on that table.
And because my automated pipeline is hard-coded with select.
The very next time your pipeline runs, the asterisk dynamically grabs everything, but everything is no longer 20 columns. It is now 21 columns.
Wow.
Your code blindly pulls all 21 columns and shoves them directly into your deployed machine learning model.
And the mathematical architecture of the model physically cannot handle that. A neural network designed with an input layer expecting a tensor shape of exactly 20 features will just catastrophically fail if you suddenly pass it a tensor with 21 features.
It is a fundamental matrix math violation. The dimensions simply do not align. Now, if you are lucky, this results in a loud failure.
A loud failure.
Yes. The code immediately throws a dimensional mismatch error, the pipeline crashes, the application throws 500 errors to the users, and you get paged at 3:00 a.m. to manually intervene and fix the broken pipeline.
Wait, a complete system crash and a 3:00 a.m. emergency page is the lucky scenario. What could possibly be worse than the whole system going down?
A silent failure.
Oh, those are the worst.
Imagine you aren't using a rigid neural network, but maybe a more flexible pipeline configuration that somehow implicitly flattens or truncates the incoming data.
Okay.
Because the new devices column was inserted into the middle of the table, all the subsequent columns get shifted over by one index position.
Oh, I see where this is going.
The model doesn't crash, it continues to run. But now, it is reading the transaction amount data and feeding it into the mathematical weights that were trained to understand usage.
That's a disaster.
It gets worse. It is reading a string of text and feeding it into weights meant for a geographic coordinate. The model is blindly executing matrix multiplications on entirely shifted, misaligned data.
Oh, that is absolutely terrifying. The model will start generating wildly incorrect, completely hallucinated fraud predictions. But the system monitoring tools will show that everything is running perfectly.
Precisely. You could be automatically declining legitimate customer purchases or letting massive fraud slip through for days or even weeks before a business analyst notices a bizarre drop in revenue.
And the damage to the business could be catastrophic. All because of a single asterisk.
All because of the asterisk.
So the architectural consequence here is that relying on dynamic wildcards couples your ML model way too tightly to upstream database changes. How do professional teams decouple this? Like, how do they bulletproof the pipeline?
They enforce strict data contracts through explicit projection. The golden rule of ML engineering is this. In any automated production environment, you must explicitly declare every single column your model requires by name.
So you actually write out select transactionid, userid, amount, timestamp from transactions?
Yes.
Every single time.
Because if you explicitly name those 4 columns, it doesn't matter if the upstream data engineering team adds 1 new column or 500 new columns to the table.
Exactly. Your query remains hermetically sealed. It will only ever extract and return the exact 4 columns you requested, guaranteeing that the tensor shape your model receives remains absolutely stable. That is exactly it. Explicit projection ensures schema stability for your downstream consumers. You use the asterisk for human exploration on your local machine, but you use explicit column declaration for machine automation and production.
That distinction is incredibly clear.
But, your point about human exploration brings us to another mechanical roadblock. We established that enterprise tables can have billions of rows.
Yes, billions.
If I am doing that initial manual reconnaissance and I write select from users just to look at the schema, the database is going to attempt to retrieve all 1 billion rows and send them over the network to my local SQL client.
It will diligently try to fulfill your request, yes.
Mm-hmm.
And in doing so, it will likely max out your machine's RAM, freeze your SQL client, consume a massive amount of network bandwidth, and,
Let me guess, trigger an alert.
oh yeah, it'll potentially trigger an alert to the database administrators that someone is executing a massive, unoptimized, full table scan. They will not be happy.
Which brings up the immediate problem of how we safely peek into the abyss. Like, if I need to see the structure of the data, but I literally cannot load the volume of the data, what is the mechanism to bridge that gap?
This is where we introduce the limit clause. It is a structural safeguard built directly into the SQL engine.
How does it work?
By appending the word limit followed by an integer at the absolute end of your query, you constrain the execution engine. If you write select from users limit 10, you are fundamentally altering how the database processes the request.
So it doesn't process the whole billion rows and then just chop off the end for you. It actually stops working after it finds the first 10.
Exactly.
Huh.
From a computational complexity standpoint, it transforms a massive full table scan into a highly efficient, nearly instantaneous operation. The engine reads the first 10 records from the disk, immediately halts execution, and returns the payload.
So it requires almost zero compute and zero memory overhead. It's like checking the seasoning on an industrial-sized vat of soup. You don't need to drink all 500 gallons to know if the chef put enough salt in it.
No, please don't do that.
Right, you just need to take a single 1-ounce spoonful from the top. The limit command is that spoonful. It gives you the structural context, you see the column headers, you see the formatting of the text, you see whether the numbers have decimals. all in a fraction of a millisecond without stressing the infrastructure.
The soup analogy is spot on. Limit provides a representative structural sample.
Uh-huh.
However, we do have to recognize the limitations of that spoonful.
What do you mean?
Well, once you've used limit 10 to safely view the columns, you might notice a column named user country. In your 10-row sample, you might see the values USA, USA, Canada, USA, and Mexico.
Okay.
But as a machine learning engineer, looking at 5 instances of North American countries tells you absolutely nothing about the global distribution of that billion-row table.
Oh, right. I have no idea if the application is only live in those 3 countries or if there are actually like 195 different countries buried deep within the other 999 million rows.
Exactly.
And I really need to know that because I can't design my model's architecture based on a random guess, which means I need a way to scan the entire column and extract only the unique, diverse variations of the data without pulling down all the duplicates.
This brings us to a massively important tool in the SQL arsenal, the distinct keyword. It is designed specifically to solve the problem of unknown cardinality,
Cardinality meaning?
meaning the number of unique elements in a set.
Got it. So how do we implement it in the syntax?
It modifies the select command directly. You write, select distinct country from users. When you execute this, the database engine will scan the entire column across all billion rows.
But it doesn't send back a billion rows.
No. Instead of returning a billion values, it uses internal hash maps or sorting algorithms to filter out every single duplicate. It only returns a clean, deduplicated list of the unique values it encountered.
So the output is just a tight vertical list. USA, Canada, Mexico, Japan, Germany, and so on. If there are exactly 42 unique countries in the entire database, the query returns exactly 42 rows.
Correct. And understanding this isn't just a matter of curiosity. In the context of machine learning engineering, executing distinct seat is a mandatory prerequisite because it directly dictates how you will mathematically encode your categorical variables.
Categorical variables, let's pause and build a really robust mental model of what those are, because this is where the Python programmer mindset has to transition into the machine learning mathematical mindset.
Yes, this is a huge leap.
In basic Python, a country like Germany is just a string. It's just a sequence of text characters.
Right, to a standard software application, Germany is just text to be displayed on a screen. But machine learning models do not read text. Neural networks, linear regression models support vector machines. They are fundamentally mathematical engines composed of massive matrices.
I only speak math.
Exactly. They only understand continuous numeric values, where the magnitude has intrinsic mathematical meaning. For example, an age of 40 is mathematically twice as large as an age of 20. The model can multiply those numbers, calculate gradients, and adjust weights.
But the magnitude of a category doesn't exist. You literally cannot mathematically multiply Germany by 5.
No, you cannot.
You can't subtract Canada from Japan and get a meaningful numeric result. They are discrete states, not continuous numbers.
Precisely. Because the algorithms only speak math, we have to act as translators. We have to mathematically encode these text categories into numeric representations before they ever touch the model. And you cannot build that translation layer if you do not know exactly how many unique categories exist.
Let's trace that workflow. Let's say we run select distinct country from users, and we discover there are exactly 3 unique countries in the dataset: USA, Canada, and Mexico. How does knowing that exact number 3 change what we engineer?
If you know there are exactly 3 categories, you can implement a technique like one-hot encoding. You program your pipeline to look at the single country column and expand it into 3 entirely new, separate columns. Is USA, is Canada, and is Mexico.
Ah, I see. So if a user's from Canada, their row would have a 0 in the is USA column, a 1 in the is Canada column, and a 0 in the is Mexico column.
Exactly. You have transformed a single string column into a 3-dimensional mathematical vector composed entirely of ones and zeros.
And neural networks love ones and zeros.
They perfectly digest arrays of ones and zeros. It can assign mathematical weights to each specific country. But here is the critical architectural constraint. To build that one-hot encoder, your Python code needs to know in advance that it must create exactly 3 new columns.
Because if it doesn't know the exact cardinality, it doesn't know the shape of the matrix it needs to construct. If we skip the distinct query and just guessed based on our limit 10 sample, we might only build a 2-column encoder for USA and Canada.
And what happens when a new country appears?
Right. During training, the pipeline hits a user from Mexico, the encoder doesn't have a column for it, and the matrix math just crashes.
That is exactly the failure mode. Using distanced allows you to map the entire categorical landscape of your dataset so you can pre-configure the exact mathematical dimensions of your feature engineering pipelines.
Okay, so we've established how to project our columns, how to protect our production systems from schema changes, how to sample the data efficiently, and how to map our categories.
Hmm?
Now we need to talk about the physical organization of the rows themselves.
Yes.
And this introduces a SQL clause that seems deceptively simple, but has massive implications for AI, the order by command.
Deceptively simple is the perfect description. On the surface, order by is just a sorting mechanism.
Right.
If you want to view the users who signed up most recently, you append order by sign date DSC to your query. The DSC stands for descending, meaning the largest, newest, or most recent records are sorted to the very top. Conversely, ASC, or ascending, puts the smallest or oldest records at the top.
If I'm building a dashboard for the marketing team, sorting makes perfect sense. Humans need data sorted chronologically to read it effectively, but algorithms aren't humans.
True.
A machine learning model processing a CSV file doesn't care if row 1 is from 2024 and row 2 is from 2020. It's just going to process the math on both rows independently. So why does sorting the data in SQL actually matter to an ML engineer?
To answer that, we have to discuss the single most dangerous, insidious trap in predictive modeling.
Oh, wow. Okay.
It is an architectural failure so severe that it routinely costs companies millions of dollars, and it all comes down to a concept called temporal integrity.
Temporal integrity. Okay, let's break that down. Temporal obviously refers to time. What does integrity mean in this context?
Well, the vast majority of high-value machine learning models are predictive. They are attempting to forecast an event that has not yet happened. You are building a model today to predict user behavior tomorrow. To train that model, you feed it massive amounts of historical data. You show it user behavior from Monday, Tuesday, and Wednesday, and you train it to predict what happened on Thursday.
That makes intuitive sense. You learn from the past to predict the future.
But here is where the integrity part becomes critical. When you construct your training data set, you must absolutely guarantee with mathematical certainty that the features used to predict Thursday's outcome contain strictly past information from Monday, Tuesday, and Wednesday.
And if they don't?
If, through a bug in your SQL query, information from Thursday afternoon accidentally bleeds into the features used to predict Thursday morning, you have completely shattered your temporal integrity.
And when the timeline bleeds like that, it triggers the trap you mentioned earlier.
Yes. When future data bleeds into the past training features, you have committed the cardinal sin of data science. Data leakage.
Data leakage. I won't spend a significant amount of time unpacking this because it is notoriously difficult for beginners to grasp until it basically destroys their first project. Walk me through a highly detailed, concrete example of how leakage physically occurs and why it is so fatal.
Okay, let's look at a classic industry failure. Predicting hospital readmissions. A hospital wants an AI model to look at a patient's medical chart on the day they're discharged and predict whether that patient will be forced to return to the hospital within the next 30 days.
That's a very standard, high-value predictive use case.
Exactly. So a junior data scientist writes a SQL query to pull the historical training data. They pull thousands of past patient records. The features include the patient's age, their blood pressure, the medications they were given, and so on.
Sounds solid so far.
And the target they're trying to predict is a Boolean column, readmitted within 30 days, which is true or false.
Okay, making sense.
But the junior scientist isn't careful with their table joins, and they accidentally include a column called secondary discharge date. This column records the date the patient left the hospital after their second visit.
Oh, I see the chronological flaw immediately.
If a patient was never readmitted, that column is completely blank. It is null. But if a patient was readmitted, that column contains a date. Because the scientists didn't sort and visually inspect their data chronologically, they don't notice this. They feed the entire data set into a complex neural network.
Then what does the neural network do with that?
The neural network is an incredibly efficient optimization engine. It doesn't care about blood pressure or medications anymore. It immediately discovers a massive statistical shortcut. If the secondary discharge date column has a date in it, the patient is always readmitted. If it is blank, they are never readmitted.
So the model essentially finds the answer key buried inside the test questions.
Exactly. It's predicting the outcome using a piece of data that only exists because the outcome already happened.
Wow. During the testing and validation phase on historical data, The model will look like an absolute miracle.
Oh, it will boast 99.9% accuracy. The junior scientists will present it to the executives, they will celebrate, and they will deploy the model into the live hospital system.
And what happens the next morning when a real patient is actually being discharged?
Catastrophic failure.
Yeah.
When the live patient is standing at the discharge desk, they haven't gone home yet. The future hasn't happened. Therefore, it is physically impossible for them to have a secondary discharge date. That data does not exist yet.
So the model just breaks.
Worse, the model, which relied entirely on that leaked future data to make its predictions, suddenly has no idea what to do. Its accuracy will plummet to worse than a coin flip, rendering the entire project useless.
That is a brilliant and terrifying example. You deploy a model thinking it's a 99% accurate genius, but it's actually just a cheat who peeked at the answers and has learned absolutely nothing about the underlying medical patterns.
Exactly.
So connecting this back to SQL, how does the order by command actually prevent us from falling into this trap?
Order by is the diagnostic instrument you use to manually audit your timeline. Before an engineer trusts a dataset, they will write a query like select from patient records, order by admission date ASC limit 100.
Okay.
By forcing the database to present the rows in strict chronological sequence, the engineer can visually scan the features across the timeline.
So they can manually verify the chain of causality. They look at the events of Monday and ensure nothing from Tuesday has snuck into the columns.
Precisely. They are auditing the temporal boundary. If they see a secondary discharge date populated before the primary discharge is even concluded, they immediately identify the data leakage.
That's fascinating.
Order by transforms from a simple cosmetic sorting tool into a critical mechanism for verifying the foundational logic of your predictive pipeline.
The architectural consequences of these basic SQL commands are just massive when you apply them to ML. Okay, let's keep expanding our mental model. We've extracted our columns, checked our timeline, and mapped our categories. As these columns leave the database and enter the Python environment, they officially become what we call model features.
Right.
Now, in many enterprise databases, the raw column names are incredibly cryptic or purely systemic. A column might just be named var73 or timestamp2. If we feed those raw names into our ML framework, the downstream code becomes unreadable.
Absolutely. Feature governance and maintainability are massive parts of ML engineering. If your Python pipeline is operating on a feature named var73, the next engineer who inherits your code 6 months later will have zero semantic understanding of what that data represents.
Yeah, that's a nightmare.
To solve this, SQL provides a mechanism to rename columns dynamically during the projection phase, using what we call aliases.
And the syntax for that is quite intuitive, right? We just use the AS keyword.
Yes. If the raw database column is called TS2, but in the context of your machine learning model, that data represents the user's last login, you simply project it with an alias. Select TS2 AS last login timestamp from users.
And the database doesn't actually change?
No, the underlying database schema is not altered at all. But the payload returned to your Python script now possesses a clear semantic label.
Which makes the Python code infinitely more readable. But applying an alias seems even more critical when we aren't just extracting raw data, but actively engineering new data directly within the SQL query.
Oh, that is where aliases transition from being a best practice to an absolute technical requirement.
Give me an example.
A significant amount of feature engineering happens right in the SQL engine through aggregations. Let's say you want to create a brand new feature that represents the total number of purchases a user has ever made. You would write an aggregation query using the count function, something like select user count from transactions group by usered.
If I run that exact query, what does the database engine actually name that newly generated column? It didn't exist before, so it doesn't have a structural name in the schema.
By default, most SQL dialects will assign it an auto-generated system-level name. It might output the column header as count star, or col1, or x0.
Imagine trying to debug a complex XGBoost model, where the top 3 most important features are named x0, x0, and x2. It would be a total nightmare. You wouldn't know if x0 was the total purchase count or the average session length.
It would completely paralyze the development cycle. So, to establish strict feature governance, you immediately bind an alias to the calculation. You write select userid count, as lifetime purchase count from transactions.
Oh, nice.
Now, that specific mathematical calculation has been permanently tagged with a semantic identity.
Mm-hmm.
The alias lifetime purchase count becomes the official name of the feature as it flows into the ML feature store and eventually into the algorithm.
It's like giving your engineered feature its official birth certificate.
Yeah.
You are formally declaring its existence and its purpose to the rest of the engineering team.
Exactly.
Now, establishing the names of our features is crucial, but earlier, when we discussed one-hot encoding and categories, we touched heavily on the fact that ML models only process math. This implies that beyond just looking at the values in a column, we need absolute certainty about the formal systemic data types of those columns. How do we inspect the underlying mathematical structure?
Visual inspection using limit is notoriously dangerous for this specific task. If you run a select query and look at a column named zip code, you might see the value 90210. To a human brain, and even to a dynamic language like Python, that immediately registers as a number. It is comprised of digits.
Right, it looks like an integer, so the assumption is that we can treat it like an integer.
But in the strict, statically typed world of database architecture, visual appearance is entirely irrelevant. We need to know how the schema explicitly defines the memory allocation for that column. Is zip code defined in the database as an integer, or is it defined as a varchar, which is a string of text?
Why does that invisible structural difference matter so fundamentally to the ML model? If it sees 90210, why does it care how the database stored it?
Because data types serve as strict boundaries for mathematical logic. They determine the mathematical transformations that the ML algorithm is actually permitted to apply.
Okay, walk me through that.
Let's explore the catastrophic implications of getting this wrong with the zip code example. If the database explicitly defines zip code as an integer, and you feed it directly into a linear regression model as an integer, the algorithm will treat it as a continuous, quantifiable numeric value.
Meaning the model will assume the numbers have magnitude and relational logic?
Exactly. The model will mathematically assume that a user with a zip code of 90210 in California is somehow mathematically greater or larger than a user with a zip code of 1001 in New York.
Oh, wow.
The model will try to calculate the variance between them. It will literally subtract one zip code from another, attempting to find a gradient.
Which is completely absurd. Zip codes are not magnitudes. They are geographic labels. They are distinct categories that just happen to be written using numerical characters. Subtracting New York from California doesn't yield a mathematical insight. It yields pure, destructive noise that will poison the regression weights.
Precisely. If you mistakenly treat a disguised category as a continuous integer, your model will hallucinate correlations that do not exist in reality. Conversely, if you have a transaction amount stored as a string, the model won't be able to calculate an average or a sum because it doesn't know how to do arithmetic on text.
It'll just fail.
Yes. You have to know the precise data type of every column so you can cast or transform them correctly before training. Core data types you must intimately understand include integer for whole numbers, float or double for continuous decimals, string or varchar for text categories, timestamp for chronological data, and Boolean for binary true-false logic.
So if visual inspection with select and limit is too dangerous for determining these types, what is the exact command engineers use to bypass the data and look directly at the structural blueprint?
You step outside of the standard select paradigm entirely. Instead of querying the data payload, you query the database engine's metadata.
How so?
Depending on the specific SQL dialect you are operating in, whether it's PostgreSQL, MySQL, or Snowflake, the command is generally describe table name or show columns from table name.
And the output of that command isn't a list of users or transactions.
No, it returns a table about the table. It provides a definitive structural glossary. It lists every single column name on the left, and immediately to the right, it explicitly prints the assigned data type, int, varchar, timestamp, Boolean.
It completely removes human guesswork from the equation.
Exactly. You look at the describe output, you see that zip code is listed as an int, and you instantly know, I need to write a transformation step to cast that integer into a categorical string before I one-hot encode it, otherwise my model will treat it as a magnitude.
That is the level of rigorous defensive engineering required for production systems. This has been an incredibly deep breakdown of the foundational toolkit.
It really has.
We have select to explicitly project our required tensor shape, the asterisk as a temporary manual reconnaissance tool, limit to computationally protect our hardware while sampling, distinct to map the exact cardinality of our categorical variables, order by to forcefully diagnose temporal leakage, aliases to strictly govern our feature semantics, and describe to uncover the invisible mathematical boundaries of our data. How do we synthesize all these disparate tools into a single, cohesive mental framework? Like, what is the step-by-step workflow a listener can take to their job tomorrow morning?
Let's construct a sequential mind map of the initial data exploration workflow. Picture this as a mandatory pre-flight checklist that you must complete every single time you are handed a new data set before you ever open your Jupyter Notebook or ML pipeline.
Okay, step one.
Step 1. You arrive at the database table. There's a complete black box. You know nothing about its scale or contents.
Got it. Step two.
Step 2. You establish visual context safely. You execute a select, coupled with a very strict limit 10. You visually inspect the resulting spoonful of data to understand the general formatting and identify potential features.
Nice and safe. Step three.
Step 3. You explicitly lock down your projection. You discard the asterisk, look at the headers you just sampled, and write a new query that explicitly names only the columns that contain viable predictive signals, immediately reducing the dimensionality of your problem space.
Okay, trimming the fat. Step four.
Step 4. You diagnose the cardinality. For every column you've projected that represents a state, label, or geographic location, you execute select distinct to mathematically map out exactly how many unique variations exist. This informs your downstream encoding architecture.
Ensuring the math works. Step five.
Step 5. You lock down the math. You execute describe to definitively verify the schema's data types, ensuring you don't accidentally treat a categorical zip code as a continuous integer.
Perfect. And finally, step six.
Step 6. You audit the timeline. You use order by Y on your timestamps to visually verify chronological progression and ensure future data is not bleeding backward into your historical features.
And if an engineer diligently executes that six-step checklist?
The output of that checklist is absolute structural mastery of the dataset. You have mapped the terrain. You now possess the deep technical context required to begin engineering complex features without the constant fear of silent mathematical failures or temporal leakage.
That is an incredibly powerful and practical framework. And I want to pause and seamlessly connect this micro-level workflow back to the macro-level architecture we established in Lecture 1 of this SQL for ML series.
Oh, definitely.
We laid out a comprehensive end-to-end feature engineering pipeline tracing the journey from raw, chaotic enterprise tables all the way to a pristine, mathematically encoded feature table ready for algorithm ingestion. We listed the overarching phases, starting with tables, moving to projection, then filtering, followed by joins, aggregations, transformations, window functions, the overarching SQL pipeline, and finally, the polished feature table.
Exactly, and this deep dive definitively proves why projection and structural exploration absolutely must occupy step number 1 in that macro pipeline.
You cannot execute step 3 filtering out invalid users if you haven't yet projected the columns that define what a user even is. You cannot join two tables together if you don't know the data types of the keys you are joining on.
Right. You have to put on the sound engineer's headphones, isolate the vocal tracks, and define exactly which signals are entering the mixing board before you apply any complex audio effects.
Let's run through one final rapid-fire practical synthesis to really cement this mental model. Imagine you and I are sitting at a terminal, and we are tasked with building a model to predict user churn. We are handed a table called subscriptions.
Okay, I'm with you.
We execute our safe preview query, select subscriptioned, userid, monthly fee, start date status from subscriptions limit 10.
Okay, the payload returns and renders on our screen. We see a clean grid. The first row displays subscriptioned, 1001, userid, 55, monthly fee, $14.99, start date, 2023-01-15 and status active. The second row shows subscriptioned, 1002, userid, 89, monthly fee, $9.99, start date, 2023-02-01 and status canceled.
Now, a junior developer just sees text on a screen, but an ML engineer's brain instantly applies the framework we just discussed. When you see that output, your mind should immediately begin architecting the pipeline.
Yes.
You see userid and monthly fee, and you instantly recognize the potential to engineer a new aggregated feature representing the total lifetime revenue per user.
Right. And I look at the start date column, and my brain immediately flags it.
Yeah.
I must use order by on this date to ensure temporal integrity, so I don't accidentally train my model on users who signed up after the churn event I'm trying to predict.
Spot on.
I look at the status column, seeing active and canceled, and I know I must immediately run a distinct query to see if there are other hidden categories like paused or delinquent that require entirely different mathematical encodings.
Exactly. You are no longer just reading data. You are analyzing the raw mathematical materials of your future algorithm. You are anticipating the matrix transformations. That is the critical mindset shift.
It really is.
This has been a phenomenal, comprehensive breakdown of the bedrock of data engineering. Let's do a highly focused recap of our core architectural takeaways before we wrap up this session.
Sounds good.
The select statement and its surrounding ecosystem of clauses, the asterisk for temporary exploration, limit for computationally safe sampling, distinct for mapping categorical cardinality, order by Y for diagnosing temporal data leakage, aliases for strict feature governance, and describe for exposing mathematical boundaries. These are the essential mechanisms for dataset projection and extraction. The overarching lesson today is absolute. You simply cannot build a functional, reliable machine learning model without first intimately deconstructing and understanding the structural shape of your underlying data.
I couldn't summarize it better myself. Throughout this entire session, we utilized projection to answer a singular vital question regarding our architecture. Which specific columns do we want to extract from the database? We mastered the art of slicing the data vertically to isolate our signals. But establishing that vertical slice logically forces us to confront the next equally massive architectural challenge.
And what is the nature of that next challenge?
We now know exactly which columns we want, but which specific rows should be granted entry into our training dataset.
I see the pivot. We've defined the attributes, but not the subjects.
Precisely. Think about the massive scale we discussed. Do we really want to train our highly sensitive predictive model on every single user record in the billion-row database? What if a massive segment of those users are test accounts created by the QA team?
Or what if half of the users haven't logged into the platform in over a decade? Should those inactive, outdated rows be allowed to influence our algorithm's weights?
Exactly. What if we were trying to build a targeted model that only analyzes recent high-value transactions above a specific dollar threshold? We have mastered slicing the data vertically. We now require a robust mathematical mechanism to slice the data horizontally.
That is the perfect logical bridge to where we are heading next in the curriculum. Today was dedicated to selecting the right variables. The immediate next step is selecting the right training examples. So in the next lecture in our series titled How Data Gets Filtered, Finding the Right Training Data SQL for ML Engineers L3, we're going to dive deep into the specific SQL filtering operations, the conditional logic that dictates exactly which rows survive to make the cut and which rows are systematically left behind.
It is going to be an incredibly crucial discussion for establishing data quality. But before we officially sign off from this session, I want to leave you with a final, highly practical thought experiment to mull over.
Okay, let's hear it.
Throughout this deep dive, we have discussed the catastrophic dangers lurking within raw data, from the pipeline crashing threat of unexpected schema mutations to the silent, invisible killer of temporal data leakage. This raises a critical operational question for you to ponder.
Yeah.
If you were dropped into a new enterprise role tomorrow, and you were immediately handed access to a completely undocumented, entirely unknown database table containing 10 billion records, knowing everything you now know about tensor shapes, temporal integrity, and categorical encoding. What is the very first highly specific SQL query you would type into your terminal to ensure you don't accidentally compromise the foundation of your first predictive model? How do you safely take that very first step into the dark?
That is a phenomenal architectural question to ponder. Think deeply about how you would sequence your initial investigation to protect your pipeline. And with that thought experiment, we will officially wrap up today's deep dive. Make sure you open up a SQL terminal and actively try the exercises to build that physical muscle. Memory, query syntax, and pipeline architecture are disciplines you master by actively typing and failing, not just by listening to theory. Write any specific technical questions you have down in the comments. We actively want to hear where your pipelines are throwing errors, what structural analogies clicked for you, and what advanced concepts you're still curious about. And of course, please like, share, and subscribe to keep systematically building your ML engineering skills with us. See you in the next one.